Good morning. So, how is the homework coming? How many people have all three of them? How many have two? Yeah, the third one is really tricky. It takes a lot of sussing it out to figure out how to make that work right. But it's good for your brain to struggle with some puzzles, and that's what a lot of these things remind me of is working some sort of a puzzle. Well, the third one, if you're struggling with, excuse me, the third one, if you're struggling with it, we can kick it around during office hours today if you want. Office hours on Fridays are at 2, and I can maybe nudge you in the right direction. But basically, it's a problem that you have to make a bunch of masks to tell whether something was that came in was positive or negative, and then build up these ways of detecting whether you had positive overflow or negative overflow, and then build up a way of combining that into saying whether you had overflow at all. And then the real tricky part is once you got all those little snippets of information built up, combining them together into a big expression that produces the result that you want, either the addition of the two variables or Tmax or Tmin, depending upon which things happened, whether you didn't have any overflow or whether you had positive overflow or whether you had negative overflow. So you have to build up an expression that turns into that value correctly, depending upon what happened. So that would be my hint, is to build up the step by step pieces of information you need. If the two variables that came in were positive and the addition of them looks negative, you had positive overflow. If your two variables came in, both looked negative when they came in, and you added them and it looks positive in the result, you had negative overflow. Okay. Yeah, they're signed because they're ints. The int type is a two's complement number, right? Well, it's tough when, it'll take some doing to get that to work exactly right. So today we're going to move on to floating point numbers and how they're represented in the computer. We've looked at unsigned and signed integers and issues involved with moving them between different sizes of shorts and ints and things, and expanding, sign expansion, extension, and truncating. We've looked at overflow and underflow and all sorts of issues involved with playing around with integer numbers and how they're stored in the computer. And now we want to learn how the floating point numbers are stored in the computer. So we're going to look at these topics of what are fractional binary numbers, what do they look like, and then what is this floating point representation standard that we use, which is a standard from the IEEE. The IEEE is the Institute for Electrical and Electronic Engineering and is one of the two main uh, computer societies that publishes journals in the computer science field. The IEEE Computer Society, the other one, of course, being ACM, the Association for Computing Machinery. So between the two, that's where all the main big computer science journals are that people want to publish papers in. So we'll look at that examples of how we store things in the computer, the properties, ranges that it has, that sort of thing, and then some rounding considerations and what happens when we add floating point numbers and multiply them, and then how do we specify and deal with all this in the C language. So first thing is, what is this binary number? Well, we know to the left of the binary point, I have to watch myself and not say decimal point because that wouldn't really be correct, would it? It's not a decimal point, it's a binary point. So the numbers to the left, good old positional notation, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? That's putting a 1 in there represents adding in a weight of that positional value. Well, just like when we have fractional decimal numbers we write down, the same thing applies here. When you go to the right of this binary point, this is how many 2 to the minus 1s do I have? You know, this is 2 to the 0 to the left. This is 2 to the minus 1 or a half, 2 to the minus 2, a fourth, 2 to the minus 3 or an eighth. So it's the same old positional notation that you're accustomed to writing decimal numbers. When you get to the point, you got the negative exponents for the position weights over here, right? So this number would be a 1 plus a 2 plus a 8, right? So this is 11 point, and then this is a half, and that's an eighth, right? So this is 11 and 5/8 in decimal, or written as a fraction. Any questions about that? Positional notation, the same regardless of the base of the number system, right? So we look at the picture and we have our halves and our fourths and our eighths and on and on and on. 2 to the minus j, where we go out j positions there. And then to the left, it's just what you think it is, 2 to the first, 2 to the second, 2 to the third, those kind of things, right? As you go to the left. So to express that, you have the summations. K goes from minus j to I, from right to left, of b sub k, the whether I have a 0 or a 1, add something in or don't, times 2 to the k. So k is just varying from minus j to I. And so that's the essence of positional notation, right? That's just expressing it as a sum all this rod up, and that's what the thing is. So let's look at some examples. We have 5 3/4. Well, here's our five, a one and a four. And here's a half and a fourth. So that's 3/4. Stop me if you have any questions. Raise your hand, write a chat, whatever. This one, 2 7/8. Well, there's our two. And then we have a half, a fourth, and an eighth, which is 7/8. One quick way to do it without adding up a half, fourth, and an eighth is to look at that number and say, oh, binary, that's 7. And this last position is an 8. So I have 7/8. This one is wrong, right? That's 63/64. That certainly can't be that because I've got a 1, right? So what is the correct answer for this one? A half, a fourth, an eighth, and a 16th, right? So that would be 7/16. Wonder if editing is turned on. Yeah. So a fourth plus an eighth would be 3/8 plus a 16th would be 7/16, right? So observations. Divide by 2 is shifting. How does the non-decimal 1 affect this? You mean this 1 on the left of the binary point that? Oh, yeah, I'm sorry. This is 1 and 7/16. It's pretty early in the morning for me. Good call. So there's the 1, and then on the right, there's the 7/16. Of course, you could write it, as 23/16 or whatever the heck you wanted to put there, right? So is that what you were asking, Colin, or were you asking something else? You good? Okay. So just like if we wrote decimal fractional numbers down, if we start moving the decimal point to the left or the right, you move it to the left, you're multiplying by 10. You move it to the right, you're dividing by 10. Same thing happens with base 2. Moving the binary point to the right would be dividing. Moving it to the left would be multiplying by 2 now, the base, right? So numbers of the form 0 dot blah, 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 a bunch of ones or whatever are, and then this little 2 means base 2, are things that are real close to 1, right? They're just adding up a bunch of fractional parts till you get up to real close to asymptotically approaching the more positions you would have, but you never quite get to 1, right? So you're adding up a half, a fourth, an eighth, blah, 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 1/2 to the I, summing all that up, getting real close to 1. So we could use a notation for representing this to say this is 1.0 minus some epsilon, depending on how small epsilon gets, depends on how many of these digits we stick on the right over there, right? So how do you add odd fractional values? What do you mean by odd? You mean they look strange or odd in the odd even sense? So the odd even sense, yeah. So, like a third, for example, is that what you're asking about? Well, there's certain things you can't exactly represent. You can get real close to them, but you can't exactly represent them in binary floating point numbers. Of course, that's true in decimal too, right? It's just different ones. And we'll look at that in a second in a lot of detail as to how that shakes out. So here's your third. So you can really only exactly represent numbers that are the sums of some x over 2 to the k type things. Other rational numbers would end up having a endlessly repeating bit representation. So our buddy a third here, we've got a fourth plus a 16th plus a 64th plus a 256th plus a 1 over uh, a 1024th. And then, so you can't quite ever get exactly a third, but what you're getting is this 0 1 thing just ends up repeating endlessly to get closer and closer and closer to a third, however many positions of precision that you have in the available width of the word on the computer. And so a fifth shakes out to this thing, this 0011 endlessly repeating. A tenth, which is just point one in decimal notation, right? You can't quite represent that exactly in binary. So you end up with 000110011001 and then you have 0011 that repeats endlessly after that, right? So whatever base you pick for your number system, there are going to be things that you can't exactly represent, but you can approximate them with whatever degree of precision you have available. That's true of any number based system. Same thing would happen with two thirds and three tenths, those kind of things. You'd approximate them, but you wouldn't ever have an exact representation for them. You'd end up with, at some point, running into some pattern that just endlessly repeats on the end of it. So, how do we actually store floating point binary numbers in the computer? Well, historically, back in the days of the old mainframe days and mini computer era, that time frame, manufacturers of computers just sort of invented their own standard for how to store the floating point numbers. And so if you were doing something on an IBM mainframe, then you wanted to port your program over to a UNIVAC mainframe or something, this created an issue because the precision and the rounding effects and things behaved a little differently depending upon what computer you were running it on. And so doing scientific computation was a little squirrely because of this. You wouldn't always get the same exact result depending upon which computers you were running it on. And so people didn't care for that. So the IEEE said, well, why don't we come up with a standard for storing floating point numbers in the computer, and then we'll have everybody, kind of rally around the flag and adopt this standard. And that's what happened. So nowadays, anybody that builds computers doesn't just ad hoc invent their own floating point representation. They implement the IEEE 754 standard. IEEE just gives numbers to their standard. So we want to learn what the IEEE 754 standard is for how these things are stored in the computer. So in 1985 is when they said, let's establish this one common standard, and then when you build your hardware, everybody will conform to the same floating point standard. And so the way they did this is, I don't remember the guy's name, but there was a guy, I think I think he was in the math department down at UC Berkeley. May have been in the computer science department, but I think he was in the math department. He ended up heading up a team of people that came up with this standard that we all use now. And the overriding motivation for what this standard would look like and how it would behave was that it would have nice numerical properties, which will become clear what we mean by numerical properties later, as opposed to a standard that would be easily implemented in hardware, or could easily see how you could implement it fast to function quickly in hardware. So that wasn't really their overriding goal. Their goal was to come up with a standard that had these nice numerical properties that we like it to have, and then say, okay, hardware designers, you figure out how to make it actually work fast. And so that has, since 1985, there's been endless amounts of uh, work and revision and processor design to take this particular numerically oriented standard and come up with a way to do it fast. But it's still uh, one of the slowest things you can do on a computer is to use the instruction that does a floating point divide. Doing a floating point multiply is just slightly less onerous than doing a floating point divide, but those are the most expensive opcodes on the computer in terms of the number of clock cycles it takes to complete them after accessing memory. Accessing memory can be several orders of magnitude slower than running any other instruction on the computer, which we'll go into in gory detail later. So, anyway, what is this floating point standard? Well, the general idea is we're going to have a bit out in the front that's going to represent the sign. And so, if the whole thing represents a negative number, we'll have a 1 in this bit position. And if the whole thing we're representing is a positive number, we'll have a 0. So a kind of a version of sign magnitude in this case. And then we'll devote some bits to encoding the exponent and some bits for encoding the fraction. Well, that looks pretty reasonable, right? That's the kind of things you'd have to do. So they're expressing that as -1 to the s. Of course, if s is 0, you get 1 there, and if s is 1, you get -1. So that's just saying, is this bit a 1 or a 0? It's negative or positive, right? And then we have the number is like what we used to call the mantissa in old days when I was in school, but now they want to call it the significand. But they still write it down as M. And then you have 2 to some exponent. Well, that's how you would express any floating point thing in binary. You remember what they taught you in school, and maybe they called it scientific notation or something, where you would write, 3.14 times 10 to the 27 or something, right? You'd always have one thing to the left of the decimal point and then a bunch of stuff to the right. And then you'd have a exponent that moved the decimal point to the left or the right to get the actual number you were trying to represent. So you could put them all in that normalized form, right? One digit to the left, everything else to the right, and then some exponent. So that's what this is trying to get at. You have some mantissa and you have some exponent. You do the same thing in binary, write everything in that standardized form. And then we want to look at how do we take that thing and stuff it into the computer. So the exponent field is going to represent this E, this exponent, but it's not quite as straightforward as that. We're just not going to take this E thing and stick it in there. We're going to store it in a different sort of way that we'll see for a certain reason. So we're trying to represent this, but the E is not really what's stored there. It's a converted version that represents that E. And the fraction is representing this M, but depending upon whether we're using what's called normalized form or non-normalized form, denormalized, I should say, this may not be exactly just M. So there's a little confusion here we have to watch out for, but I'll explain it all to you how it works. So we don't really store the E here. We store something else that represents the E. We don't necessarily store the M. We store something that kind of represents the M. So depending upon the precision that we're working with, single precision, double precision, or this crazy Intel extended internal precision thing, you get a different number of bits dedicated to hold the exponent and the fraction. So our 32-bit floating point numbers, like if you declared a float in C, this is what you would get. If you declared a double in C, you'd get that double precision floating point, right? So the numbers you have to remember are in the 32-bit, you got 8 bits for the exponent, which leaves you 23 bits for the fraction. When you go to the 64-bit, you get 3 more bits for your exponent, so that makes 11. So you got left over 52 bits of precision to hold your fractional part. So 8 bits, 11 bits, and then the other is just a consequence of that. You always have 1 for the sign bit. Okay, so there are going to be 3 different flavors of how we store the floating point number. We're going to have one flavor called normalized forms. Then we're going to have another one called denormalized. And then we're going to have a third flavor called special cases. So the first one we want to look at is storing floating point numbers in normalized form. When we store normalized form numbers, you can tell that the floating point value being represented is in a normalized form because you look at the exponent, the exp field, right? And it is neither all zeros nor all ones. So anything sitting in exp that is not all zeros and not all ones means, oh, this is stored as a normalized form floating point number. The exp field, what is actually stored in there is you take the exponent e that you're trying to represent in that m times 2 to the e thing on the previous slide. And what you actually store in there is something that has a bias applied to it. And the reason we're storing this thing, this exp field, as the e with a bias applied to it, is because we have a need to store both positive and negative exponents. Well, we could have yet another sign bit inside the EXP field, or we could store the EXP field as a two's complement representation for positive and negative things. But we don't do either of those. We store it as the um, exponent we started out. We store it as a exp minus the bias is equal to the e that we want to represent, right? Now, what is the bias value? Well, our desire here is to come up with assigning half of the values that we would encode in the exp field to represent positive exponents and half of the values to represent negative exponents. So the bias, if I have k bits in my exp field, the bias is 2 to the k minus 1 minus 1. So in the case of a 32-bit single precision floating point number, the bias that's going to be used is going to be 2 to the 7th minus 1. 2 to the 7th is 128 minus 1 gives you 127. So the bias that's used for the single precision floating point numbers is 127. In the case of the double precision, where I have 11 bits, right, 2 to the 10th is 1024. And if I subtract 1, I get 1023. So the bias that's used in encoding the EXP field in double precision is 1023. We'll look at some specific examples in a second and see what the actual numbers look like. This is just the scheme that we're going to use. Now, for storing the significand, the fractional part, think about putting something in that quote scientific notation form like you learned in school with decimal numbers. 3.14. You always have one thing to the left of the decimal point. Well, if we did the counterpart in binary for that, you'd always have one thing to the left of the binary point that would be a 1, right? That would be the normalized form. 1 point whatever times 2 to some exponent, positive or negative, to get you the number. Well, since that thing to the left of the binary point is always a 1, unlike in decimal where it can be one of 9 different values, it can only be one value. So then why store it? So when we go to store the significand, we've got the thing in a form of 1 dot bunch of bits to the right times 2 to the some exponent. We're going to store the exponent in a form here. And when we go to store the significand, we just store the bits to the right of the binary point. There's an implied 1 to the left. We get one more position of precision. Don't use up one of our bits to represent that thing that's always 1, in other words, right? So we get an extra leading bit for free because there's always, it looks like 1 dot something all the way up to 2 dot minus some epsilon, 1 dot whatever bits are out here. If I had all 1 bits, I'm getting real close to 2, but never quite get there, right? So that's the range of things I'm going to store in my normalized form, right? We get an extra bit for free by not storing that leading 1 there. So enough of this. Let's look at an example. So we get our favorite number, and our favorite number now is apparently 15 213 base 10. There it is, sitting in base 10 as a decimal floating point number with a dot zero tacked on to the end of it. So in binary, 15,213 is all this gibberish, right? All these weights for that positive number. And if we wanted to put it in our normalized form, it would look like what? The leading one dot all this rot, and then I got to have 2 to the 13th to move the dot all the way back over to here, right? So the dot needs to go all the way over to here to get back to what I'm really trying to represent. So there's my binary thing in a normalized form. 1 dot all this rot times 2 to the 13. So that being the case, the fractional part, the significand, this 1 dot all this stuff, we're going to have an implied one. I'm not going to store it. And then we just take the fractional part and put it in our 23 bits that we have. And there it is sitting in there. And then our EXP field, we're going to take this 13 that we need for the exponent, for the E value, right? The bias is 127, as we've seen when we have this 8-bit EXP field in single precision. So if I take the 13 and I add it to the bias, I get 140. And so that's what I store in there. So the way you interpret what's sitting in the EXP field is you take it and subtract the bias from it to get what it really represents. So why in the heck are we doing that? Well, you can't put all ones in here because that wouldn't be a normalized form, but you could put all ones down to here and have a zero there. If you take that number, the biggest thing you could stick in there, and subtract the 127 from it, right? You get the biggest positive exponent we can store. And you can't put all zeros, but you could put all zeros and have a one in the right. And you subtract the 127 from that, you get the smallest negative exponent. So we're trying to cut the thing in half and say half of these numbers represent positive exponents, half of them represent negative exponents. The way we achieve that is by subtracting a bias from the number that's actually stored in there so that half of them show up positive, half of them show up negative for what they really mean, right? So that we put 140 in there because if you take 140 and you subtract the bias from it, you get the E, the thing we're really trying to represent. So that's the scheme for what we call a normalized form floating point number, what it looks like. Has anybody got any questions about that?
Can you explain again how the frac became so long?
Well, we've got a 32-bit word, right, where we're going to store this thing, right? Single precision is going to use a 32-bit word to store the thing. So the way that the bits are parceled out in this encoding form is 8 bits are going to get gobbled up to hold the EXP field. 1 bit's going to be the sign of the overall number. So that's 9. So I have 23 bits left over in this 32-bit word to hold the fraction, right? So there's my 32 bits. To represent this stuff, I don't need all of them. So they just have zeros out on the end of it, right? Does that make sense? Every
Yes, thank you.
single precision floating point number is stored in 32 bits, right? 8 of which represent the EXP field and 23 of which represent the fractional part. there's an implied one sitting in front of this fractional part. So this is what we call the normalized encodings. And those are the ones where this EXP field is neither all ones or all zeros, right? And when you have neither all ones or all zeros, you take what's in there, subtract the bias from it. For 32-bit precision, it's 127. So I'd subtract 127 from this number that's stored there. That would give me my actual E field for the exponent. This says it's a positive number. And then I would take 1 dot all this stuff and then move the dot over 13 positions. And then I've got the value that this whole thing actually represents. Normalized floating point number. Now, the denormalized ones is the case where the EXP field contains all zeros, right? The other one being when it's all ones is our special values case. So the denormalized representation of these numbers is going to be EXP is all zero. And the way you interpret the bias or the meaning of the EXP field is different now from the way you interpret it when it's a normalized form. So if the EXP field is all zero, the actual E value that we're representing is minus the bias plus one. Well, in the case of the 32-bit representation, that's going to be minus 127 plus one is 126. So the E value for every denormalized form in single precision is always minus 126, right? We'll see why that is in a second, or maybe tomorrow, Monday. The significand coded with the implied leading zero. So we don't have the implied one like you had in the normalized forms. It's a leading zero now. So when we have all zeros in the EXP field and all zeros in the fractional field, what would that represent? Well, this EXP in the denormalized form always represents, for single precision, an exponent value of minus 126. There is no leading zero, so this is 0 dot bunch of zeros. Oh, and if you take the minus 126, you move it to the left 126 positions, and what you get is all zeros. So that is the value 0, right? That's how zero floating point looks. It's a denormalized form, and it's all zeros, and the sign bit would be 0. So that works out pretty cool because my representation of 0 is all 0 bits. And that's very comforting, right? If I have zeros in my EXP field, it's a denormalized form, but the fractional part has some ones in it somewhere. What those things are representing are numbers that are very close to 0, right? Because you're putting a bunch of 1 bits in there. There's a leading 0 in front of the binary point, and then you're having this minus 126 value here, which is doing what? Moving the binary point to the left 126 positions. Then you're tacking on whatever the things are in the 23 bits of the fraction. So that's a number that's real small number that's close to 0, both plus and minus, depending on whether I flip the sign bit on at the beginning of the number. So they're numbers that are real close above 0 and numbers that are real close to 0 below 0. So we'll look at the properties of this thing in a second. The third thing that we have is the case where the EXP field is all ones. If the fractional part is all zeros and the EXP field is all ones, this is representing infinity for us. So positive infinity would have the sign bit of 0, negative infinity would have a sign bit of 1. So we just have this special encoding that we can use to represent an infinitely large number, or a number bigger, in reality, a number bigger than we can actually encode in this encoding form. Would get kind of like your saturating ad example. When it gets bigger than what we can encode, it turns into infinity. That's a special case. Now, this all ones in the exponent when you don't have all zeros here is our encodings for not a number. And in reality, we really would only need one encoding for not a number, but we got scads of them, right? Because all possible combinations of those 23 bits in single precision are also just meaning not a number anytime you have all ones in the exponent. So what would what would not a number be? Well, maybe if I did some arithmetic operation on the computer and I was trying to do square root of 1 or something, or I was trying to do, infinity times 0, or subtract this infinity from infinity, or try to divide something by 0 or something. All those things that doesn't mean anything mathematically, right? They'll result in not a number, right? So we need some way to say what you did doesn't even produce a number, right? So those are our special cases, plus or minus infinity and not a number. And those are indicated in the case where the EXP is all ones and the infinities are the zeros. The not a numbers are anything other than 0. So now we look at the way these things lay out on the number line. We know that 0 was our denormalized form number, all 0 bits, right? And then our denormalized numbers are going to be um, positive denormalized ones, getting bigger, just close to 0, and the negative ones getting this direction. And then at some point, which we'll see what at that point is, it flips from denormalized forms into normalized forms. And you can think of, uh, if you looked at the encodings for these floating point numbers and interpreted all the bits that were in there just as it was a big magnitude number and sorted them, this is the way they would sort, which is a numerical property that we want it to have, right? Only the negative ones would sort highest because they have the 1 bit flipped on. And so all those negative numbers would sort highest, and then we'd get here, and we'd flip into positive numbers, and they would sort below. But the plus infinity would sort highest. It'd have all 1 bits in the EXP field and then zeros, right? So it would sort here, and then those not a numbers would sort there, right? Because they have non-zero values. So anyways, that's one of the numerical properties we wanted to have. So let's run out of time, but we'll we'll conquer this by looking at some make believe sizes, like we don't want to have to deal with these big monster 32 or 64-bit things. Let's look at some, pretend we have just an 8-bit representation and use the same scheme and see what the things would look like. It's easier to deal with, right? Using the small ones, right? So we'll do that Monday. We'll start looking at some examples and see how these encodings shake out and how you get your zero values and your um, denormalized values and your normalized numbers and see how they work out. Okay. So we'll go through all this Monday. We'll do it with a small 8-bit representation so we can actually write the numbers down conveniently. So this is our first blush of IEEE 754 floating point numbers, and this is how they're actually stored in the computer. When you store 3.14 decimal in the computer, you're getting an encoding using this scheme to stuff that into memory. And when you pick up things and multiply them or add them or whatever that are floating point values, you're using these encodings, and it's shoving these encodings into the circuitry that does floating point multiply and floating point divide. Okay. Go back for a sec. Back where here? This one. How far back you want to go? The special values. These guys? Yeah. So the way you tell it's one of the special encodings is the EXP field has all ones in it. Remember our normalized form, the EXP field can't have all ones and it can't have all zeros. It has all the other possible values in there. If it's all zeros, it means it's the denormalized form. And if it's all ones, it means it's one of the special values. And so we reserve the encoding of all ones in the EXP field and all zeros in the fractional part to symbolize infinity, and then flip the sign bit on or off to mean positive or negative infinity. If it's all ones and not all zeros in the fractional, that's an encoding that means not a number. Is that what you want? Okay. So I guess see you office hours, or I'll see you Monday morning. And good luck on your homework and have a great weekend. Looks like the weather's nice. Get some fresh air, some sun on your skin. Take care. Bye bye.